now we think about the basis function and the regression spline and the smoothing spline and generalized additive models. And for the first three things, so the basis functions and the regression spline and the smoothing spline, we will use the Nile data. So remember that the Nile data is available in default, the R package. So Nile data is time series data from 1871 to 1970. So 100 observations, and the plot, maybe Nile. Okay. Yeah, so this is the Nile data. So we are fitting curve. So this is the line graph. So probably the level goes down in the first maybe 30 years or so. Then after that, almost flat. Possibly it goes up a little bit. Maybe in detail, maybe we have a little more pattern. Maybe here, going down, maybe going up a little bit. Then one spike. Then after that, yeah, almost flat. Maybe then increasing a little bit. So maybe the little more complicated function fits better than the simple straight line or quadratic curve. So yeah, so we are fitting curve. So maybe time. Okay, maybe scatter plot looks better. So this is 1871 to 1970. So plot of time Nile looks better. So we fit some curve here. So the curve is represented by the summation of, linear combination of sine curves. So that is the basically the Fourier, the series, the expansion. So it's good to use the cosine and the sine curve. So this is not periodic curve, but if this is some periodic time series, such as the daily temperature or something, then it's certainly good to fit the cosine and the sine curves. So now that we define the 4 trigonometric function, maybe cosine and the sine and the actually with the period of maybe 100 and also period of 200. Okay, so we try. Okay, so just that we normalize it, we subtract 1870 and times 2 pi and 200. So this makes a cosine curve with the period of 200, I think. So 2 pi is the one period. So if we divide the cosine curve by 200, the period is 200. So we define the sine curve also. Usually we need the 2 curves on the same frequency because we have the phase in addition to period. So that to represent the arbitrary, the shift, the parallel shift of sine curve, basically we need the 2 curves, right? So that is clear by addition formula in the trigonometric function. So C1 and S1. And also that we use the cosine curve and the sine curve with period, the half of 200, so 100. So this has the period of 100 and also S2. S2 is sine. So we use these 4 functions to fit the data. And yeah, so this is not really necessary, but we want to standardize it. So just that we adjust to the level. So we can include the intercept to tell this, but just for demonstration purpose that we think about the cosine curve and sine curve with whose mean is the mean of the Nile River water level, and also some reasonable size of fluctuation, just to compare the original plot and these sine curves. So this is just for demonstration purpose. So just normalize the versions. So C1, C2G, C2, and S2. Okay, so basically we prepare the cosine and sine curves. And yeah, so this is the graph, and we can overlay these 4 lines. For example, lines of C1G. The x coordinate is time and the C1G and the color 1. Okay, so now that we have this. So this is the cosine curve with the period of 200. So this is just a half of the period. So if we go here, and after 100 years, it goes back to original level of around 1,200. So we've used this basis function so to fit the Nile variable. But of course, the only one curve that does not really explain the shape. So we use also this one. So we use linear combination of these 2 curves to represent this trend. So basically, if we use these 2, we just have the parallel shift of the sine curve with the period of 200. And we use higher frequency curves also. So basically, we use these 4 basis functions to explain the trend of this data set. So in polynomial regression, we use the straight line and the quadratic curve, cubic curve, and the quartic curve to fit the data. But here that we use these 4 cosine and sine curves. So it has some benefit. At first, it's good if it's periodic. And second, the value does not blow up when time goes to infinity or time goes to negative infinity. So if we use, for example, cubic function, sometimes we have problem to just extrapolate for 20 years. But the sine curve and the cosine curve, since these are just periodic functions, we don't have much trouble if this go beyond 1970 or go before 1870. Yeah. So then, okay, so we prepared these 4 functions. So now that we want to fit the data. And yeah, so this is just a linear regression, right? So we have just 4 variables, and we fit the Nile River water level on these 4 variables. C1, S1, C2, S2. So the C1G, S1G, C2G, and the S2G, these are just for demonstration purpose. So we use these 4 figures, these 4 curves. But just for regression, basically intercept and this magnitude doesn't matter. So just we put C1, S1, C2, S2. Then AIC of LP2, yeah, we have the 1,274. This is the comparable to the previous results, maybe. Not really. Yeah, so last time that we do step functions, we use step functions to approximate this Nile River level, and just the fixed, not fixed knots, the 2 knots, 3 knots, and 4 knots. The minimum is 1,271 or something. So this is pretty good. It's slightly worse than that, but it's much better than, for example, step function with the 2 knots. 3 knots, maybe it's 3 knots. It's yeah, it's slightly worse. Actually, slightly worse. Step function, the 4 levels. We have the AIC of 1,271, so it's slightly worse, but not much worse. So yeah, we can plot this. So line time fitted LB2 and maybe color 5 maybe. No, sorry, error. Oh, lines maybe lines. Yeah, it's a little bit hard to see, but the light blue is the fitted curve. So this is linear combination of the black, red, and blue and the green curves. And you can see that it represents the overall shape of the plot. Maybe it's a little bit hard to see, so maybe line with 3 or something. Then it's slightly better to see. So the level is higher here, then lower here, and going up a little bit. So you can see that this is a good fit for this plots. So this is how the basis functions work. So basically, this is a linear regression. Just we prepared different functions, not polynomials. The polynomial is problematic that when x goes to larger or x goes to smaller. And also that we have multi-collinearity that when we fit x squared, x cubed, x to the 4th power, 5th power, these functions are very similar, for example, on interval 0, 1. Okay, so this is how the basis functions work. Do you have questions? Yeah, we have several ways to overlay graphs. Maybe you want to use the ggplot2 package or the usual graphs. And the usual graphs that we have the a kind of high-level function such as plot. This basically generates everything. And also the low-level function such as lines. So this just adds something to the existing graph. So in this case, we make a plot. Then after that, we added the 5 lines. Okay. So now that we do the regression splines. Okay, so this result looks good, very smooth, but slightly worse AIC than step function. Okay, so now regression spline. .4, and we use the Splines package. Yeah, so our packages are developed at many places. So many people develop packages. So maybe some newer packages are available. But okay, so this is a standard classic package for regression spline. So regression spline, remember that this is piecewise cubic functions. So if we have 4 sections, then we have cubic function on each section, each of the 4 sections. But we need just smooth transition. We have the 3 knot points. For example, we have knot points here and here and here. So piecewise cubic, but those cubic functions are connected smoothly. So what does it mean, smoothly? So smoothly means at first it's continuous, and also it has the derivative at the knot point, and also the second derivatives are the same at the knot points. So that's the smoothness. So library, and we specify knot points. So it's hard to optimize knot points, but we just choose the 3 points which equally separates the interval. So the 3 knot points that separates the entire time period into 4 equal parts. So then this is the knot points. I don't know, maybe 1895.5 is a better knot point. I don't know, but okay. So now that we just for now that we use this, and the basic regression spline that we use the BS function, time knots xi. Yeah. So this is the basis function. So this is just the first 6 observations. So just the 1871 to 1876. So if type this, then we have all of this, maybe. Yeah, so these are 6 figures. Maybe it's a little hard to see, so maybe round BS, maybe 2 BS1. Yeah, then we can see. So these are basis functions. So the first one is starting at 0, then getting larger, then getting smaller. So these are the bases that they used. So this is basically, yeah, so cubic function, piecewise cubic function, the 6 of the cubic functions. I'm not exactly sure how they defined these functions. So obviously some of them starts later than 0, later than the first time point. But actually the second one starts pretty quickly. So I don't know what basis they used, but basically this is the piecewise cubic function. So they just transformed a little bit from the explanation in chapter 7. So they use these 6 functions to fit the response variable. And yeah, then we fit the data. So so we name something the regression spline. So LRS, and we use still the linear regression, and we use this basis spline function. So this is the 3 knots, the cubic spline. Then you can see the AIC value here. So we have the 3 knots, then we have the AIC of 1277. Actually, it's worse than the last time. We have 3 knots, so that means, so how many parameters? We have the 4 pieces. So okay, so we separate the original time period into 4. So on the most left-hand side, okay, so we have cubic function. So we have 4 parameters. Then we have 1 additional parameter when we go beyond the knot point. So 4 plus 1 plus 1 plus 1. So 7 parameters. But still, the AIC is the 1277. So it's not as good. Yeah, actually, the 7 is obvious from here because we have the 6 basis function and plus intercept. So we have 7 parameters. So maybe we plot this again. Time Nile. Again, this is the scatter plot, and we add fitted value of this spline. So this, yeah, this looks similar to the previous, the fitted curve by basis functions of cosine and sine. But yeah, here it's higher and the value is lower here and going up a little bit. This is pretty unnatural shape, but we don't have much flexibility. So yeah, usually spline is more unstable towards the end of the x, the range of x. So if the x is larger or smaller, it's unstable. Here it's not really unstable, but if we extrapolate, probably it's unstable. So this is cubic function. So this pattern, probably it goes down and down and down if the time gets smaller and smaller. And this is cubic function, but the coefficient of x cube is opposite, so negative. So probably this also goes down. Yeah. But overall, the fit is not really good for this case. Yeah, you can also add fitted the confidence confidence band for this one. If we get the standard error, so prediction. So if we put the LRS then yeah, we have the fitted value and also the standard error of fitted value. So if we use this standard error, then we can get the confidence band for this fitted curve. So we have this one, but also that we can add lines, time, predictor fit plus 2 times predictor. Actually, predicted fit. This is the same as the fitted, but we have another way to describe this way in this way. And line type 2 is the dashed line. So this is the upper bound of the confidence band, and the lower bound that we got -2. So plus minus 2 using normal approximation basically covers 95% of the cases. So this is confidence band. So not 90%, 5% of observations are within this band, but actually with 95% probability, the true curve is within this band. Yeah. So if coefficients changes slightly, then the fitted value at the end has wider variability. Right? For example, if the coefficient of x cubed changes a little bit and x is very large, then the difference gets larger. So that's why the confidence band is wider towards the end, also here. But this is the 95% confidence band. Yeah, so any method is unstable if the x value, predictor value is near the end. Yeah. Any questions or comments so far? Okay, so now that we have another way. So I'm not exactly sure how these two are different, but also the NS function instead of BS makes almost the same thing. So we have the time and the df6, and also we can specify the knot points, so knots but in NS function. But if we use NS, basically again we have the 6 basis function, which is the piecewise cubic functions. So if we use this ns function, basically we can get the same result. And ns function have different bases. I think these 6 bases are orthogonal. So just the different linear transformed version of the 6 variables. So I would like to just describe these curves. So originally we have this curve. So just we only use the, okay, so this is the original data set. And yeah, maybe time ns time df 6, just this first column to 6th column. One, two, three. Sorry, this has different scale. So okay, so just ignore this part. Just ignore this part. So basically, we have 6 functions, and we don't overlay, but we describe just the 6 functions. So just some specification here. So this is the first function of this, the output of ns function. So this is the piecewise cubic function. So one example of piecewise cubic function. And the second function is this, and this is, okay, so maybe color 2. Maybe we want to add this on the original pane. So this is the second one. So this and this are orthogonal probably. So if we think about the center probably around here, and if we think about the correlation between x and the first one and the second one, it becomes 0. So for example, if the center is around here, then around here, red is negative, black is positive. Around here, both are positive, and here red is positive, black is negative. So the overall the correlation becomes 0. So if we describe the other curves, so these are 6 curves. So actually, in the handout available in Canvas, these 6 curves are all black. So it's really hard to see which corresponds to which. But the black goes from here to here, and the red one here, green one here, and the blue one is here. We have negative values, and the light blue, this one, and the purple here. And these are orthogonal, I believe. So it uses the QR decomposition. So these bases should be orthogonal. So yeah, so they use these 6 curves. Yeah. I'm not exactly sure that how they make these 6 the decomposition to achieve orthogonal basis. But anyway, our interest is final fitted curve. So we don't really care about these 6 basis functions. So if we change basis, it looks different, but the fitted curve are the same as the previous one. Yeah, maybe we used the default, the knots in ns function. So that may not be the same as the regression spline that we described with using BS function. But if knots are the same, basically the basis should be the same for both these two methods.
So the NS function generates the nodes automatically on its own, right?
Yeah, I think that in both cases, probably we can do. Maybe we can try BSK in the same way. BS, yeah. I don't know what happens here. Yeah, still, it's strange. So BS time. Okay, so BS time, we just. I think the default is 2 knots in this BS function. It may depends on the sample size, but yeah. So help BS. Yeah, so we have the same options. The BS also if we can skip knots and we can specify the number of knots. So if the BS3, basically we should have the same thing as the NS result. Yeah, so, and also NS, I think that we have the same options. NS also we can specify the number of knots or degrees of freedom. So yeah, just I introduced NS and the BS differently, but basically it works in the same way. So their way to transform this basis functions are different, but basically these two are the same. Just think about the two people work on the same project and they slightly coded it differently. So the intermediate products basis functions are different between the two. Okay, so now the smoothing splines. Smoothing spline, we use the smooth.spline function. So we name it SS. So format is a little different. So the time is X and Nile is Y. We fit Nile on time. Then we specify df is equal to 2. So this is equivalent number of degrees of freedom. So basically it corresponds to the straight line, and 2 is straight line. So fitted S1, SS2. Yeah. So these are fitted value. So yeah. So plot time Nile and lines. This is probably just SS2 color 1 straight line here. Yeah. But the degrees of freedom gets higher. We have more flexibility, so this line will not be smooth. So for example, SS, we define SS4 as smoothing spline with DF4, then curve is this. And you can see this is probably not the cubic function. So this is piecewise cubic function. And it has the same smoothness as cubic function, but the specification is a little different. Okay, so basically smooth, so piecewise cubic function. So we have 100 data points, so we have 99 knots. Then we define the cubic spline. Then after that, we add some penalty term so that this curve is not fluctuating too much. So then this is the fitted curve. So this is the piecewise cubic curve with 99 knots, but we have some restriction, so it looks smooth. Or SS6. So again, this green curve is piecewise cubic function. We have 99 nodes. But we have the effective degrees of freedom is equal to 6. So we penalize the too much movement. So the curve looks smooth. If this df, the effective degrees of freedom, is larger, then it's more flexible and more ad hoc curve than this. So at this point, maybe this blue curve is reasonable, but if we go too far, maybe 30, probably the situation is different. And 35. So obviously the light blue curve fluctuates too much. Probably it's not good for prediction. So it fits the data, but maybe it picks up the too many outliers or the too much of noise. So if you see this, probably the best one is maybe green curve or the blue curve, and not the light blue curve or the straight line. So this is basis function, and we can optimize. We can optimize the we can optimize the degrees of freedom by cross validation. That is done by option CV. So CV is equal to true and the time and Nile. Then actually it's pretty close to the 30, but the pink curve, pink or maybe purple, I don't know. So pink curve. So this is optimal one by cross validation. So you can see the DF30, this light green curve, probably overfit the situation a little. For example, probably these are somewhat outliers, but so it doesn't go up this much, but actually it's close. So probably the effective numbers of degrees of freedom is close to 30, maybe 20 or something. Maybe we can check this. Yeah, so equivalent, sorry, not effective. The equivalent degrees of freedom is equal to 23.4. So this is the optimal flexibility. So we need actually the 23 parameters to best represent the trend of this scatter plot. Yeah, so if you want to just get the best results, you can just type CV is equal to true, then everything can be done within R. So you can see that the data science, it really depends on the software. And if you use the good software, basically you don't have to code anything. And yeah, and before, and do you have any questions? So equivalent degrees of freedom is defined by some trace of a matrix. So basically, when we fit the model and think about specific observation, if the first observation is the linear combination of first to 100 observations, and the weight of first observation explains how the model overfits the data, right? If to explain x1, to explain the y1, if we use, sorry. So I would say that we explain the yi by linear combination of, the yi hat by linear combination of y1 to y100. Okay, so b1 y1 plus up to b100y. So if we solve this system of linear equation, if we solve this system of linear equation, then what is the BI? So if BI is large, then that model is more flexible, but possibly overfit the situation. So think about the most extreme case that the y hat of I is equal to yi. So that means that we overfit the situation 100%. So in that case, the degrees of freedom is 100. But here that we have the 23.45. So basically the 23% of y hat is explained by y hat I is explained by the yi. Okay. But other 77% is explained by other observations, so that it doesn't overfit the situation. Yeah, so now the local regression. So local regression, so the idea is that we use local information. So suppose we wanna predict the y sub 10. Then at first think about x10, then closest xi's. We choose the closest, the xi's. Maybe 10 closest, maybe 20 closest xi's to x10. Then use those 20 observations to fit the data. Yeah, and in this case we have the 20, so the 120 out of 100, so 20%. But this percentage basically the controls how we, so how how much the data overfit the data, the model overfit the data. So that is done by lowest function, the LOESS function. So Nile on time, then span is equal to 0.2. Just we specify the 0.2, then that we can fit the data. LO, oh, I think that we name it. So this function is actually the default, the package local polynomial regression fitting. So span that specifies how many percentage of observations we use, how many the proportion of what proportion of data we use. And weight, we didn't really give the weight, so probably they use just the same weight for all observations. Maybe not. Yeah, actually they use this. So we use this the cubic function, not the tricubic function. So maybe the 9th degree function to give the weight. Yeah, so some specific weight function. So basically we only use the 20% of observations, but even within these 20% that we give higher weight if the observation xi is closer to this x10 to be fit. So, yep. And we can see equivalent number of parameters, the 14.62. So yeah, basically we do the same, the equivalent number of degrees of freedom here, and we have the 14.62. So if we plot time Nile and lines time fitted LOEO, color 1, then we get this figure. So it's similar to the last one. The basis spline, the regression, no, the regression spline with the degrees of freedom 23. It's close because the degrees of freedom here is 14.6. Okay, so now that we make a different version, what happens when we change this span to 8? So this becomes more volatile or smoother? What do you think? We make the span is equal to 0.8. So that means we use 80% of the data to fit each observation. The curve is smoother or the other way around, more volatile, less smooth. How many people think it's smoother? How many people think it's more volatile?
I think it's smoother.
Yeah, smoother. Yeah, you're right. Yeah, because we use
you're using more points, so
yeah, more points. Yeah, that's right.
So you're like
that's
weighting.
Right.
Basically, you're estimating based on more points, so it's not going to be as volatile. If you did, say if you based on every 3 points, it's going to be extremely.
Yeah.
It'll fit every single data point really well.
Yes. Yeah, you're right. So especially, for example, the span is 0.01. Basically, we fit all observations, right? So that's true. So actually, much smoother. Yeah, maybe most extreme case is 0.01 and 100. So maybe LOEO 01. We have some error. Actually, we cannot really describe maybe span is too small. I don't know, 0.02. Maybe we try. Still, we have some trouble. Zero 0.02 already fit the entire data. So 0.02. So I think this is some rounding problem here. So we have 100 observations. So 1% is just one observation, but it sounds even 0.02, we only use one observation. It doesn't sound reasonable. Yeah. Span is the proportion of data points, but the parameter alpha, which controls the degrees of smoothing. Yeah. Yeah, maybe slightly different definition here. Maybe. Oh, I see. No, actually, yeah, I don't know. So for each interval, we don't take the average, but we fit the regression line for each line. So that's why we have trouble. So if we have 0.01, we only have one observation, so we cannot fit the straight line. So that's why it makes error. 0.02, we have two observations to use, then to fit the data. So we fit the straight line for two observations each time. And so I don't know what happens for that case. Maybe just the point itself and the closest observation. So, oh yeah, so that's why. So the two observations. So the straight line going through these two observations, always that goes through this observation. So that's why it fits perfectly. So basically we have the 2 degrees of freedom for each local regression. So if you have 2 data points, we perfectly fit the straight line. So the minimum possible span is 0.02. And the maximum is 1. So that should be the flat line, right? So line 1, no, dot. Slight curvature. This is the blue one, right? 1, 2, 3, 4. 4 is blue, so span is 1 and a straight line. So yeah, but still we have weight function, so it's not the straight line. So we use all observations, so it sounds like always we have the same straight line, but we have slightly different weight for different observations. So line the fitted for each data point is different. So that's why still we have some curvature here. So span is equal to 1, the smoothest. Red one, this is the span is equal to 0.8. The black one, 0.2. Green one, 0.02. So this is the local regression. So we can now fit the local regression, smoothing spline, regression spline, basis function. Okay, so now that we go to the generalized additive models. So remember that the generalized additive models, we have basically more than one predictors. Otherwise, it does not make any sense. So GAM, so GAM is here. So generally, we have the P predictors x1 to xp, and we think about y is equal to the function of x1 to xp. But this is too general to fit. So we just assume that we don't have any interaction between xi and xj. So if we have P predictors, we assume that the effects of i's predictor and j's predictor are independent. So yi is summation of beta naught plus summation of, sorry, the yi is equal to beta naught plus the summation of fj, xj. I's observation of the j's variable. So this way. Yeah, but we generalize it. So this f1 of x or f2 of x. So these are not straight line, but generally we use the smoothing spline. So the relationship between y and the xj is nonlinear, but the interaction is ignored. So this is GAM. So how to fit the GAM? So we need the more than one predictor. So we use different data set. So we use library, ISLR, and we use the GAM function. So library GAM. Then the wage data is within ISLR package. And maybe So wage data is here. So we have the year, age, marital status, race, education, region. So this is the income data for 3,000 people. We have possibly 11, maybe 10 predictors. But there are too many, so we focus on just the specific ones. We have already attached age, so we use the age and the year and education. So year and age and education to fit this wage. So yeah, so yeah, the pairs function that clarifies the relationship. I mean the scatter plot. Pairs function generates this, but here, yeah. For example, let's think about year and education. So since educational level, we only have 5 levels, and year of the survey, that we only have 7 years. So this doesn't have any information. So we can only see that all combination exists. But we don't know how many observations are here, how many observations are here, how many observations are here. So the one way to represent this kind of categorical variable in the scatter plot is that we add some noise so that we can see how many observations are around here. So that can be done by the jitter plot, the jitter function. So we have year, but we define the year.j, is the jitter one. So this makes noise. So maybe so originally this is 2006, 2004, 2003, 2003, but we add small noise. So 2006 becomes 2005.85 and 2004 becomes 2003.93. So in this way that we can see, if we use this function, that we can see some fluctuation here. Actually, fluctuation is small, so still we cannot really see maybe too many observations. But so we have, if we have the reasonably small number of observations, that we can really see how many observations are here. Maybe for education also we have to do that. Maybe education. Okay, so education is actually categorical right now. So we have to make it numeric first, then have to add the noise. So it returns an error. But generally, adding some noise is a good way to plot. Okay, so for example, I don't know. Trivial example, but if x is all 1, and y is all 2, and plot x, y, then just 1 point. But if we add jitter, then we can see these 10 points. Maybe, so maybe this is too trivial. So if x is this and the y is this and plot x, y, we only see the 10 points here and 10 points here. So we cannot really see. But if we add jitter, then we see the 10 points here and the 10 points here. Okay, so anyway, so we have pairs of this, so we use this to the data. So we can see the wage is higher when age is around 40 or 50. And the year, we cannot really see the clear trend, but probably it's increasing over time. And educational level, certainly, the higher educational level 5, they earn more than the level 1 or 2. So now that we fit the GAM model, the GAM, still that we use the linear model, LM function, but the we have several ways to do this. Yeah, so we can still use the LM function. Later, we use the GAM function to fit the data. But the one way to fit this GAM is using natural spline. And probably basis spline also works. For example, this educational level is categorical variable. So anyway, so we give many degrees of freedom. We have 5 educational level. So that means that this variable have 4 degrees of freedom. And year and wage is may have nonlinear relationship. So we have the degrees of freedom 4. And age, we give 5. So these are just arbitrary numbers. Then we can see this. So we have several parameters, 4 parameters for year and the 5 parameters for age and the educational level. So each level have the coefficient. And we can do the same thing by GAM function. Basically, we are doing the same thing, but the output is somewhat more convenient to see. So basically, we have the same format. Just we replace the LM by the GAM. We slightly use different specification. Then the GAM. And the summary, we didn't show the summary before, but the summary of GAM is actually, it's easier to see. So we just put all the year variable in the same line and all age variable in the same line. In the previous linear regression output, just we have the 1 by 1. So the first factor, second factor, the first variable, second variable, and third variable of age. But here that we just summarize the information. It's a kind of ANOVA table for LM. So it's more simplified and more to the point. And we can make scatter plot.
Sorry, Professor, why we don't have the coefficients here?
Coefficient, it should be there. Just this is how this summary looks. So yeah, somewhere you can find the coefficients. I don't know. So this is the structure of the object, the structure of the GAM2R. So coefficients, if you want to find we have coefficients here. So GAM2R, then $sign the coefficients. then actually we get the coefficients. Maybe we can compare with the GAM1. No, GAM1, no, the GAMLM, GAMLM1, GAL.
Well, the degrees of freedom are a bit different.
Degrees of freedom?
Yeah, for year
Sorry?
and age, they're a bit different between the two.
Oh yeah, a bit different. That's right. That's right. So yeah, so we have to do the same thing. So GAMLM is equal to year 2, right? Year 3, year 2 and age 3. Yeah, year 2 and age 3. Okay, so then education and okay, so then GAL MLM. So okay, so for example, 11 and 4.04, those are the same. Yeah, those are the same. Yeah. So basically, we do the same thing.
And how we define the degree of freedom for each variable? This is something arbitrary or?
Yeah, yes. So we have to optimize by some criterion, such as cross-validation. Or yeah, you can use the hypothesis testing. For example, year 3 and year 4, and we fit 2 models, and we do ANOVA, then we can compare. So, but for forecasting purpose, maybe the comparing cross-validated error or AIC is good.
Thank you.
Okay. So we have the same thing, and now the plot of GAM. I don't know. Yeah. So probably this is the convenient feature. So if just we type plot and the standard error, the truth, then we see this kind of profile of the regression model. So yeah, so this is the fitted curve for year. So year, we have the quadratic curve. Right, so here, I think the degrees of freedom is 2. So quadratic curve. So that is written here. I think this cannot be done automatically in LM function. So if you use GAM function, we can see this. So this is basically the fitted relationship between year and wage. So year is higher than wage positive. So basically, I think that the wage scale is what, the maybe 50 to 250. So actually the 4.3 points, maybe 2.5 points higher than average in 2009. In 2003, negative 4 point, so 4 point lower than the center. So this is quadratic curve. And H, there we have, I think, cubic curve, right? So probably this goes here and goes here and probably fitted curve. So like this, it looks like this, right? So it looks like this should be cubic curve. So probably looks like this, but at age 80, so ends at this point. If age 150, probably this fitted curve is like this. So maybe around age 110, the wage the hits the bottom, then going up. And if your age is 150, probably your wage is much higher. So of course, it does not make sense, but this is the fitted curve. Probably only valid between the age 20 to 80. Educational level. So this is just the categorical variable. So we put the 4 parameters, and it indicates the how much difference it has from the baseline level. Yeah. So GAM function, sometimes to see ANOVA table or these profile functions, it's easier to see the results. Yeah, and the GAM, we have used the regression spline, but also we can use smoothing spline. GAM, maybe GAM S. wage and smoothing spline age 3 plus education. So smoothing spline that we have basically the as many knots as possible, and but we penalize the too much fluctuation. So it automatically look for the degrees of freedom. Yeah. Yeah, so we compare several ones. So the GAMS and the GAM1S, maybe this has the S here. So for example, we compare these two models to see if year is really significant factor to improve the model. Then you can see if we compare these two models, actually the second one is better because this significantly better because the p-value is p-value for this added variable is less than 0.05. So in this way, we can determine the degrees of freedom by hypothesis testing. Maybe this is not the best way to determine the number of predictors, but at least we can see the additional term significantly improves the model. GAM1 and GAM2. So the first term is really significant, but the second term, the quadratic term, may not be significant. The p-value is 0.2454. I don't know if we have AIC for this. GAM1S, yeah, 2S. So it's really marginal difference. So GAM2 have slightly worse AIC, so probably the GAM1S. So this is the better, but very small difference. The difference is 0.64. So one additional parameter, so that means we have the penalty of 2 in AIC. So actually we have penalty of 2, so 29888 plus 2. So if the error size is the same, that this becomes 29890, but actually it improves a little bit. So it's really marginal difference. We cannot say which is definitely better, but the GAM1S is probably slightly better. Yeah, so either you can use AIC or cross-validation to see which is the best. Yeah, so basically this is the chapter 7. So now you can fit all nonlinear relationship. So by polynomial regression, the step functions and the basis function, the regression spline, and smoothing spline, local regression, and the GAM. So GAM is a little different because it's for multiple predictors.
Oh, could you use local regression with GAMs? Like local regression is the building blocks for each predictor.
Yeah, so the answer is I don't know, but I guess probably no, because basically the GAM is the same as linear model. So the S, we can combine GAM and S, the spline or natural spline, but basically this gives just the predictor variables. We have seen that, for example, NS year 2 just gives the 2 vectors. So that's why the GAM, they uses just those 2 vectors to fit. But if we put complicated functions such as lowest, then probably we cannot do that. Maybe we can try that, but probably we cannot do that. Lowest, what's the format? The lowest, what? Lowest yeah, I think no, because the lowest, I think the yeah, so the format is you know what? So the format was LM Y NS something, right? So that's why if we have just replace X by NS of X, still it works. But the format of lowest is local regression as Y tilde X, right? So it does not specifically give the basis functions. So I believe that it does not work with the GAM. So if you want to do that, then I don't know.
Maybe there's a function in the GAM library. I don't know.
Possibly, yeah. You can search for it. Yeah, that's a good question. Yeah, then it can possibly improve a little more. Yep. Okay. Yeah, so if you combine everything, theoretically it's better, but sometimes we cannot do that because of some statistical reasons or just because of software.